I guess, I mean, I know. But it's so problem solving. I just blood pressure.
Okay, I'll get started. Just wanted to begin with a reminder that Thursday is test 1, so we'll be in here. We have 1 hour for test 1. It has these 10 true-false questions. The lecture quizzes are meant to help in preparation for those. It has 3 long, fully worked out problems. Make sure you put down all your working out, any diagrams, any formulas that are needed. The homework, the worksheets and problems I'm doing in lecture class are meant to be preparation for that. Any questions on all of that? Yes. Yeah, you can use your calculator. You can bring your calculator. You get a formula sheet. It's attached to the end of the exam. You can see the formula sheet in one of the subdirectories in modules. Any other questions? Okay. So if you remember last class, we said that last class and this class were kind of a single story of exploring electrical circuits. In today's class, I want to talk a little bit more about solving electrical circuit problems with the concept of the idea of an equivalent resistance for the circuit. I want to talk a bit about another method for solving electrical circuit problems that uses what's called Kirchoffs rules. We'll talk about those. And then if we get time, I hope there'll be time, we're going to talk a little bit about circuits involving batteries, resistors, and capacitors that are used to charge up capacitors and discharge capacitors. So those are the topics for today. So I wanted to work through a circuit problem that is solved with this idea or notion of equivalent resistance. We'll figure out the equivalent resistance of the circuit, and then we'll use our knowledge of the equivalent resistance to figure out how to figure out the currents and the voltages through the individual components of the circuit. So this is really just an example, illustration of using equivalent resistance to solve circuits. This is the circuit. I showed you it at the end of the last class. It has a battery in the circuit that supplies electrical power, electrical energy to the circuit. It drives electrical current around the circuit. And then it has this arrangement of resistors. And this arrangement of resistors is not itself simply, an arrangement of just parallel resistors or an arrangement of series resistors. Rather, this arrangement or network of resistors is some combination of parallel components and series components. What we're going to do is figure out the equivalent resistance of this network of resistors. By figuring out the equivalent resistance of the network of resistors, that enables you to figure out the current that the battery is supplying to the circuit. Once you know the current and you know the voltage here that the battery is supplying to the circuit, you can then analyze the individual components in the circuit and figure out the fractions of the current that is supplied to any component, the fraction of the battery voltage that is supplied to any component. When we do that, we'll be using, one thing we'll use is Ohm's law to solve that part of the problem. The other thing that we'll use is some of the basis behind Ohm's law, between resistors in circuits, how they share current if they're in parallel, how they share voltage if they're in series. Okay, so on one slide, a lot of information, but this one slide is how I solve for the equivalent resistance of that network of resistors, and then actually I then solve for the current that was supplied by the battery because I knew the EMF that was provided by the battery. So I've got those two things on here, and I just want to walk through them. Obviously this is one, there's no chance of me doing this on the document camera. It would take me forever to write this out. So I've tried to lay it all out on one slide, calculating the equivalent resistance. So upstairs here is the original circuit. I redrew the original circuit, and then step by step by step, I've redrawn the original circuit, but each step down, I'm replacing resistors that are either in series or parallel with their equivalent resistance. And this is my path through the circuit, spotting locations, places where I've just got series or parallel resistors, and replacing them with an equivalent resistance to finally get to the single equivalent resistance that's equivalent to the network of however many resistors there were here. There's 5 resistors, and then that allows me to figure out the current that's supplied to the circuit by the known EMF of the battery in the circuit. So I'm looking up here with the original circuit, and what we have to do is spot some portion of the circuit, some part of the circuit where there's just resistors in parallel or just resistors in series. In this particular circuit, the location to start is over here on the far right. On the far right, we've got just these 2 resistors here, and they're in series with one another. And so that's really where I started. I think there's no other place you could start this. There's no other sort of pair or group of resistors that is just in series or just in parallel. The only location is here. And so this is an obvious place to start. We've got 2 resistors in series. The current flowing down this arm on the right through these 2 resistors is the same. They're going to share some voltage that's applied to the pair of them. But the point is their equivalent resistance is the sum, just the sum of their individual resistances. So I replaced R4 and R5, which were 5 ohms and 20 ohms, with a 25 ohm equivalent resistance. That would draw the same current for the same voltage as the 2 individual resistors. And that led me to redraw the circuit like this. So now I've just got 4 resistors. I've got the original R1, R2, R3, and then I've got this equivalent resistance that I've called R45. Now again, I'm looking at the circuit with the eye to replacing some group of resistors with an equivalent resistance. And the group that I can replace either has to be all resistors in series or all resistors in parallel. And if you look at the circuit now, the group that we can replace is this group of 3 resistors here. So R2, R3, R4, 5. It's the 10 ohm, the 5 ohm, the 25 ohm. They are all in parallel with one another. Okay? All of their upper ends are tied together by this wire. All their lower ends are tied together by this lower wire, so they are in parallel. The current that's driven around the circuit by the battery is shared between the 3 of them. The voltage between these, imagine two terminals here. This voltage here is equal across all of them. And so that's what we mean by parallel. And the rule for parallel resistances is that the reciprocal of the equivalent resistance is the sum of the reciprocals of the individual resistances. So that's going to make a smaller resistance after you do the calculation. And I wrote that calculation out here. So I'm going to call, this is very awkward notation, but my equivalent resistance is going to be R2345 because ultimately 4 resistors went into this equivalent resistance. Its reciprocal is the sum of the 3 reciprocals of these 3 individual resistors. So it's R2, R3, and then this R45 equivalent resistance. Yeah?
Why is R1 not considered?
I'm not considering R1 yet because R1, if I try to include that, well, I've made a circuit that's it's not simply parallel, and it's not simply series. So I have to, when I pick this 2 here, I found a location that was purely resistors in series. When I found this location here, this was 3 resistors that were purely in parallel with one another. I can't mix things up. Then it's going to go wrong. So that's an important point. I can't include R1 yet because it's not like another resistor in parallel with these 3. Anyway, so I do this calculation, and when I did the calculation, I won't go through all the numbers here. You can check this later. I think I'm right. I got a resistance that was 2.94 ohms for the equivalent resistance. Note, this resistance of 2.94 is smaller than any individual resistor, and an equivalent resistor for a parallel network will be smaller. Now, upstairs here, we made a bigger resistor than the individual resistors because for series resistors, the resistance is bigger than the individual resistors. Okay, now I'm going to replace these 3 parallel resistors with this single equivalent resistance. So here it is, R2345, and it's about 2.9 ohms. And the circuit now looks like this little arrangement here. Well, now we're getting a much simpler circuit. And if we look at this circuit, we quickly recognize that this is a circuit involving a resistor R1 over here on the left that's in series with this resistor R2345 over here on the right. So the current from the battery must flow through this resistor and must flow through this resistor R1. These 2 are in series. I can just use the rules for series resistances. I've just got to add the 10 ohms to the 2.94 ohms, and that's going to give me the total equivalent resistance of the entire network is this 12.94 ohms. And so that was the route through the circuit. And so, we just had to be careful about spotting when things were just parallel, resistors were just series, and just take our time to step through the circuit. And ultimately, we found the single equivalent resistance we could replace the 5 resistors with. And that's what I've done downstairs here. Here's this 12.94 ohm resistor. At this point, right, you can determine a very important thing for the circuit. You can figure out, given we know the EMF that the battery is providing, it was 25 volts in this problem, we can now find the current that it's supplying just with Ohm's law. So to find the current that the battery is supplying, I'm just going to take the EMF that the battery is supplying, which we know, and divide it by this equivalent resistance. That's applying Ohm's law basically to this resistor here, but it will tell us the current that is flowing around this entire circuit here. This entire loop that that current's being pushed by the battery, and the power of that current is being dissipated by this equivalent resistor. Anyway, if I fill in the 25 volts to 2.94 ohms, I get a little under 2 amps, 1.93 amps. Okay, so that's a big moment to, if I'm solving this problem. I'm going to have a coffee break. This is a moment to reflect. This is a moment to reflect because I've combined the network of resistors into a single equivalent resistor, and that's led me to a very important understanding. I know what current this battery of a known EMF is supplying to the circuit. The circuit problem now typically becomes just figuring out what fractions of that battery EMF, what fractions of that battery current are supplied to individual components in the circuit. So we might ask what fraction of the current and the EMF does the resistor R1 get. We might ask the same thing for resistor R2, and so on and so forth. To solve that, I'm going to show you, not for every resistor because it just wastes our time, but I'll show you for a couple of resistors on the next slide. So the way that you typically will solve the current through an individual resistor and the voltage across an individual resistor is by examining those circuits that we made in finding the equivalent resistance. So we actually made 4 circuits. We had the original one with the 5 resistors in. Then we went to one with 4 resistors in. Then we went to one with 2 resistors in. And then finally we went to a circuit with 1 resistance in. In general, all of those circuits might be handy. You might want to look back at any one of those circuits as you work through the individual resistors, trying to figure out the voltages and the currents across them. So it's useful to reflect back on those circuits you made. I'm just going to show you for R1 and R2. What's the current and the voltage through and across R1? What's the current and the voltage through and across R2? And I put it etc. The other ones you would do the same idea, the same procedure. And so I don't want to keep going through it. Okay, R1. R1's probably the easiest. R1's a good one to start with because it leads you to the solution for the other ones, the R2, 3, 4, 5, and whatever. I went back to remember I had the four different circuits. I went back to the circuit that had, was the last but one. It had R1 in it, and it had that equivalent resistance, R2, 3, 4, 5 in it. And this one's really helpful if you want to think about the voltage and the current through R1. Well, look, immediately we know the current through R1. The current through R1 is the same as the current through the equivalent circuit, which is the same as the current that went through the equivalent resistor that I called R equivalent and the battery. So this battery is supplying 1.93 amps and it passes around this loop, and that 1.93 amps is going through this resistor here. So there's no calculation to figure out the current through R1. We can just read it off our results in the last slide. It is 1.93 amps. The only calculation we need is to find the voltage across R1. What's the difference in potential between the two ends in R1? We just use Ohm's law there. Ohm's law tells us that that voltage is the product of the current, which is I1 or I, times the resistance of that resistor. So I've got 1.93 amps of current through the resistor, 10 ohms of resistance, 19.3 volts. So that was straightforward. We were just using Ohm's law and notion about currents and voltages to solve for the current and the voltage across this particular resistor. Supposing I want R2. So if I was wanting the voltage and current that was passing through R2, I actually went back to this equivalent circuit. This is the second circuit that we made. It's the one after the very first circuits. So the first circuit had 5 resistors, but we combined 2 in parallel to make R4, 5. We had this equivalent circuit here. Well, let's think about the sharing of voltages. So there's 25 volts provided by the battery to the entire circuit. We just understood that 19.3 volts are distributed across resistor R1. So there's 19.3 volts used up here. So that leaves a certain voltage, 25 volts of the battery, less than 19.3, that's 5.7 volts. That 5.7 volts, if you look here, is kind of between these two, I marked two terminals on here in blue, but it's between these 2 points, these 2 locations in the circuit. That's the voltage across the terminals of R2, because it's just connected by wires to these points. Also, it's the voltage across R3, if we wanted that. Also, it's the voltage across the equivalent resistor, if we R4-5, if we wanted to explore that. If we're wanting the voltage and the current across R2, well, this is the voltage across R2. It is 5.7 volts. So I called V2 this voltage across this resistor. It is this 5.7 volts. Again, at that point, once you've got either the current or the voltage for a resistor, then you're going to be using Ohm's law to figure out the remaining thing, which is either the other quantity, the current or the voltage. So now I've got the voltage across resistor 2. I can figure out there's a typo here. So these should be, sorry, I'll correct this. This should be I2 equals V2 divided by R2. So the subscripts should be 2's here, not 1's here. Anyway, the current through I2 will be the voltage across what about, and this 1 shouldn't be here either. I really messed this up. Gosh. This was like the 1's have invaded this equation here. All these 1's over here should be 2's, and this one here should go away because the current through resistor 2 is the voltage across it, which is 5.7 volts, and that's divided by the resistance of our R2, which is 10 ohms. So it is 5.7 volts divided by 10 ohms, and it is 0.57 amps. I must have got the finger stuck on the 1 key or something like that. It was just spraying 1's everywhere. And I'll correct this. These should be 2's, and this one here should go away. Okay. Well, other than that last little mishap, that's the procedure for solving the currents and the voltages through any of the resistors you could pick in the circuit. And as I say, I'm not going to go to them all because it's the same idea over and over again. It's a rather systematic procedure. Any questions on that? Okay, then I'm going to move on to another way of solving circuit problems. The equivalent resistance way of solving those circuit problems with networks of resistors and batteries often works, but actually doesn't always work. I'm going to show you a circuit where it doesn't work. When you've got a circuit where it doesn't work, there's another procedure, you'll be pleased to know, for solving the circuit. It uses Kirchoffs rules. There's a Kirchhoff current rule and there's a Kirchhoff voltage rule. And so we're going to introduce the voltage rule, the current rule, and then we're going to apply them to a particular problem that you can't be solved with an effective equivalent resistance. It has to be solved with Kirchhoffs rules. Okay. Take a look at this circuit. Now, this circuit has less resistors than the last circuit. There's only 3, and there's actually 1 in each of the 3 arms of the circuit. If you look, there's a top arm, a center arm, and a bottom arm. And each one of those has a resistor in it. It's a 1 ohm, a 2 ohm, and a 3 ohm here. On the other hand, this circuit has more than 1 battery. The last circuit had just 1 battery in it. This circuit has 2 batteries in it. So there's a battery upstairs here in the top arm, and there's a battery downstairs here in the bottom arm. Now you could stare at this circuit all day long, and you cannot find in this circuit any location where you've got either resistors that are simply in series or resistors that are simply in parallel. There's no such location in this circuit because in this case the batteries are getting in the way. You can't find a location where there's just a pair of resistors, for example, in parallel, or a pair of resistors in series, because any any attempt to find that also has a battery in there. So for example, look, I might say, oh look, here I am, I got a 2 ohm and a 3 ohm, and look, they look like they're in parallel with one another, but no, they're not in parallel with one another because of this battery here. So we can't isolate this piece of the circuit as a 2 ohm and 3 ohm in parallel and replace it with an equivalent resistor because the battery spoils that. And so this circuit is unsolvable by that procedure of equivalent resistances, figuring out the equivalent resistance and then figuring out how currents are shared, voltages are shared around the circuit. We need a different procedure. And that's what Kirchoffs' voltage and current rules are. So let me just say I got this slide here to say in words what the current rule is, what the voltage rule is. That they're pretty straightforward to understand what the rules mean. I got a slide or two, I think, that's coming up on a couple of things you have to be careful with. You have to be careful with directions of currents, and you have to be careful with senses of voltages, whether the voltages increase or decrease. So those are things you've got to be careful with. And then we'll move on and we'll look at an example, an application of Kirchoffs' rules. The application of Kirchoffs' rules, there's kind of a physics part to it, which is the part for us that's most important, understanding how to build Kirchoffs' rules, apply Kirchoffs' rules to the circuit. Then there's also kind of a math part to it. It's sort of equation, a problem of solving several equations for several unknowns. I'm going to focus less on the mathematical part. On a test, I might ask you something about the physics part, about sort of maybe about building, writing down an equation based on Kirchoffs' rules. I wouldn't ask you to solve 3 equations for 3 unknowns on a test, because that's a mathematical problem. It's a mathematical problem that is not really about the physics understanding that underlies it. Anyway. Forgotten what I was going to do now. Current rule, Kirchoffs' current rule. So Kirchoffs' current rule firstly says you've got to think about a junction, or what we call a node, in a circuit. So just to be clear, this green dot is a location of a node. And actually I didn't mark it, there's another node over here on the right. A node, or junction, is where multiple wires meet. And so we've got, this wire from the middle arm of the circuit meeting this wire here that connects the top and bottom arms. So that is a node. It says, the current rule says that the current that passes into that node is equal to the current that passes out of that node. That is really just a statement that you don't lose any current or create any current when you have a node. It just somehow passes through. It's kind of a statement that you don't destroy charge or create charge when you have a node. The charge just passes through. Just to give you an idea of its implementation, on this circuit here, I labeled the 3 currents in the 3 arms. So I've got I1 upstairs here, I got I2 in the center here, and I got I3 at the bottom here. I labeled their directions. I'll come back to their directions later, but I labeled I1 as traveling to the right, I2 is traveling to the right, and I3 is traveling to the left. If we think of the node over here on the right, I1 is traveling into it, I2 is traveling into it, I3 is traveling out of it. So Kirchoffs' rule says that the sum of the currents going in, which is I1 and 2, is equal to the sum of currents going out, which is just I3. So this is an application of Kirchoffs' rule for current to this node here. And this is what we'll be doing. The other rule is the voltage rule. And it talks about the voltages in a circuit. Specifically, the voltage rule talks about the changes in voltage as you walk around an entire loop in the circuit. So as an example, I've imagined this loop here. So what this almost an entire circle means is I've started, say, somewhere downstairs on this bottom arm, and I've walked all the way around this circuit through this middle arm here. And then I've come back to where I started. So that's what the Kirchoffs voltage rule applies to, a complete loop around the circuit. And like the nodes, there was more than one node, there's more than one loop in this circuit. There's actually two more. There's one around this top half, and then there's one around the whole lot. But anyway, let's take this one as an example. If I'm an electron, and I walk around that loop, I would find that whenever I met a component, a circuit component, battery or resistor, I would be either walking up in electrical potential or walking down in electrical potential. And Kirchoffs' rule said, go around the loop, add up all the potential changes as you walk around the loop, and some will be positive and some will be negative. Some will be like an upward staircase and some will be a downward staircase. Once you've got back to where you started, the sum of all those changes in potential is 0. When you walk around the entire circuit, it's 0. So, just as an example, if I'm starting on this bottom arm here, in the center of it, and I'm going to walk to the left. So, ho-hum, ho-hum, I'm an electron, and then I reach the battery. When I reach the battery, I've got to step from the negative terminal to the positive terminal. I've stepped up 4 volts. So there's a 4 volt change, and I wrote it down here. This is plus 4 volts. Then I'm walking along this wire here, nothing much interesting. Then I get to the resistor. And I walk across the resistor. So there's a change in potential across the resistor. Because, because of Ohm's law, there's current through it, so there's a potential difference. We always draw, if you remember, conventional current, which is the direction that positive charges would be moving. Positive charges roll down the potential hill. So that means that in this particular case, the positive end of the resistor, something went a little bit wrong here. These should come down here. This is the positive end of the resistor. This is the top of the hill. And this is the negative end of the resistor. This is the bottom of the hill. And so as I walk through this resistor, I'm an electron. I'm walking down a staircase. And the elevation, the distance I drop as I walk down that staircase is given by Ohm's law, is 2 ohms times this current I2. And so I wrote that down here too. This minus 2 I2 is that drop in, that's a drop in potential across this resistor here. Then I carry on walking around the circuit and I meet the 3 ohm resistor. When I meet the 3 ohm resistor, again, there's going to be a potential change as I cross the 3 ohm resistor. If I'm going in the direction of the current is rolling down the potential hill. So this is going to be a drop in potential. There's going to be a negative change in potential. And again, it's given by the product of the resistance and the current that's flowing. That's Ohm's law. And so in this case, it will be I3, that's the current that's flowing, times the 3 ohm resistor, so 3I3. And it's minus because I walked down the potential hill. These 3 changes are the only changes around this loop, and they must all add up to 0. And that's Kirchoffs' voltage rule. And so those are the 2 rules. So those 2, we applied the current rule to one node. We applied the voltage rule to one loop. And in each case, we made an equation that contained the unknown currents in the circuit. If we had applied the voltage rule to another loop, and there's 2 other loops here, we could make a 3rd equation, and then you've got this mathematical problem of 3 equations, 3 unknowns. You can figure out what the currents are. So that's the basic idea. And we will do that, but I wanted to stress a couple of points. So firstly, signs of potentials across resistors. The easiest way to get these problems wrong is to get the signs of the changes of potential wrong when you apply the voltage rule. When you walk around a loop, if you get any of the signs wrong, you're going to get the answer wrong for the currents. Short explanation of it. So you've got to be careful about the signs. Okay, so here we are. Here's an example. We're walking across this resistor in this direction indicated by this bright red arrow. And this is in the same direction as the current that's indicated here. If we walk that direction in your calculation, you're going to be walking downhill. Because remember, we denote the direction of current, imagine it's positive charged carriers, and they roll downhill. So this would be a negative change in a potential across a resistor. It would be minus IR. This is the reverse. This picture down here is the reverse. So here we're traversing the resistor. Now it's the blue arrow is us walking, or the electron moving. It's moving opposite the direction of the current. In that case, you're climbing up the potential hill. So now if you're going opposite the direction of the current, then you're going to be climbing a potential hill. The potential difference is going to be plus IR. So that's one place where you got to get the plus sign or the minus sign correct. Here's the other place where you got to get it. So we also walk across batteries in a circuit. Yes?
Okay, this was on an exam. Would we have to denote the current flow, or is that something that's given to us?
Yeah, so that's a great question, because I've assumed, I showed you the direction of the current, and you based your plus or minus sign based on that. I'm going to say more exactly about the point you're raising, because it seems to be a bit of a problem. How am I going to get the current right? It turns out that all you've got to do is you can guess the directions of all the currents and then just be consistent with it. So if you guess them all and just be consistent with it, you're going to get the right answers for the currents. If you get a positive answer for a current, you guessed right. If you get a negative answer for a current, it just means it was actually going the other direction. So because to begin with, you can't actually know what directions the currents are. You might guess it, but you might guess it wrong. So that's a very, very good question. And these rules I'm giving you here are really just about based on your guess, what is the sign. So you'll see that when we do an example. Okay, this is the rule for batteries, and this one's probably a bit easier, but because you see very clearly with the batteries. So here I am walking, this is my direction of walk, and in this case I'm walking from the negative terminal to the positive terminal. In this case, when you walk across a battery, that's an increase in potential, so you want to get this sign right. So this would be a positive change in potential. Here's the other case. Here I am walking, this is my direction, or the direction of the electron. In blue here, it's going from the positive terminal of the battery to the negative terminal of the battery, so that's going down in potential. So we've got to get that right too. Okay. So those are things we're going to bear in mind. Now we're going to solve a problem with those two rules, and we're going to come to the excellent question here about, to get the directions of the potentials for the resistors, I need to have a direction for the current. And I said you can guess that direction for the current, and that works. So this is a circuit we're going to solve. We've got 3 resistors in it. They're different values now, 35 and 20 ohms. We've got two batteries in it, arranged with these polarities, and they have 20 volts and 10 volts. And we're going to calculate the 3 currents that are flowing in this circuit. There's a current in the top arm, a current in the center arm, and a current in the bottom arm. So we're going to calculate those 3 currents. The way that we're going to calculate those currents is by 3 currents is by creating three equations. Now, I just wanted to show you this, first of all, that in principle, on this circuit, are actually, there's two nodes, so this one over here on the left and this one over here on the right, that you could apply the current rules to. And there's actually three loops. So there's a loop, a big loop around the entire circuit, and then there's two smaller loops around the bottom half and around the top half. So there's actually 5 locations you could apply Kirchoffs rules to. And in principle, you could write down 5 equations. Now, we only need 3. We only need 3 because we only got 3 unknowns. So that's the first thing. We just need to write down 3 equations. Another important point is that the node over here and the node over here, they involve the same currents going in and out. Those 2 nodes do not give you 2 independent equations. So there's only, you could pick the one node on the left or the node on the right. It's going to give you effectively the same equation. So what we've got to do is we typically use one node because the node equation tends to be a very simple relationship between the currents. And then we pick 2 other loops. And you can sort of pick 2 other loops, I like this loop. You might want to look at which loops have less components in them, because less components means, less chance of getting the potential difference sign wrong or something like that, or less work in adding up all the potential differences. Okay. Finally, the point about the direction of the currents. You don't know the direction, in general, you wouldn't know the direction of the currents when you start out this problem. In general, when you start out the problem, you're going to just guess the directions of the currents. And as I say, if you guess right, you'll get the right value of the current and you'll get a plus sign. If you guess the direction wrong, you'll get the right size of the current. You just get a minus sign, which means it was heading in the opposite direction. So you've also got it right, really. Okay, so in my solution, I guessed these 3 directions. I guessed that on the top arm of the circuit, the current is going, if we follow I1, it's going left to right. On the middle arm, it's also going left to right. And on the bottom arm, it's going from the right to the left. So these are the 3 directions of the current I guessed. And when I started this, I had no idea. I didn't even spend any time to think about it. I just guessed them. Now, once I had guessed them, though, then I can say which is the more positive potential end of a resistor, which is the more negative potential end of the resistor, based on the direction of these currents. So if you look upstairs here, for this resistor here, this current's flowing left to right. It's going to be flowing downhill. So this is the more positive end. This is the more negative end. Same thing for this resistor in the center. The current is flowing left to right. So this is the more positive end on the left-hand side. This is the more negative end on the right-hand side. For the resistor downstairs here, the opposite is true, because this current is going from right to left. It's going in the other direction. So this is the top of the potential hill on the right. This is the bottom of the potential hill on the left. So I denoted those just because it might be easy for me when I'm writing the equations just to look. I've figured out the senses, the polarities, the potentials on the resistors. Okay, so I guessed and then I used the guess. So now I'm going to make 3 equations. This is the step in which I make the 3 equations. So there's not much new on this sketch, on this slide, although it's packed with information. This is the circuit again. And remember, I've labeled the directions of the currents and the polarities of the resistors. But also on this sketch, I'm showing you what junction and what loops I'm going to use in solving the problem. So I'm going to use this junction here. So I'm going to apply the current rule to this junction here. It's written down here. And then I'm going to use 2 loops. I'm going to use this loop, the bottom loop here in light blue, and I'm going to use this outer loop here in whatever this is, orange. And as I say, you're just going to use one node. It could be the one on the left and one on the right. You end up with the same equation. There are 3 loops, and you can pick any 2 or 3 in solving this problem. I tell you why I did pick this one in blue and this one around the entire circuit. This arm downstairs here is a little bit simpler. So it's got only one component in it, rather than the other 2 arms have 2 components in it. So I said to myself that if I make my loops involve, both of them involve this lower arm, right, that's less changes in potential. So just trying to save myself time. I wanted to watch a show on TV, and so I picked these pairs of loops. Okay. Here are the 3 equations that come out of the one node and the 2 loops. So look, as I mentioned, the junction rule, or the current rule, tends to lead to a very simple relationship between the currents. And so that's always a good one. I always kind of favor the junction rule, current rule. In our case, it simply says that the current going in, which is I3, must be matched equal to the currents coming out, which is I2 and I1. So I1 plus I2 equals I3. So that's easy enough. What about the walk around the blue loop here? Well, if you walk around the blue loop, you're going to go through the battery that I labeled epsilon 2. You're going to go through the resistor R2, and you're going to go through the resistor R3. So we're going to go through these 3 components. And that's what you see downstairs here in the equation. The battery, epsilon 2, the resistor R2, the resistor R3. The sizes of the changes in potential are the potential across the battery, so that's epsilon 2. IR for the resistor R2, IR for the resistor R3. The signs are important. So I went up in potential as I walked across the terminals of the battery. I went down the potential hill as I walked through resistor R2. And then I also went down in potential as I walked through I3. And so that's the plus, the minus, and the minus. Exactly the same business for the other circuit, the loop that goes all the way around. This is going to go through battery number 1. It's going to go through resistor number 1. And then it's also going to go through that resistor R3. So I'm going to have 3 terms. Look, 1, 2, 3. When I go through the the battery epsilon 1, there's a change in potential that's 20 volts. I go through resistor R1, there's a change in potential I1 R1. When I go through R3, there's a change in potential I3 R3. When I walk this clockwise direction around the circuit, I'm going to go up in potential through the battery, and then I'm going to go down in potential through resistor R1, and also down in potential through resistor R3. And if you look at the equation, that's how I arranged it. 3 changes in potential going up through the battery, down through resistor R1, down through resistor R3. And those are my 3 equations. Any questions on that? Because that's kind of like, that's the physics is over, really. I've made 3 equations by understanding the properties of the circuit and how currents flow in a circuit and how voltages are shared in a circuit. That's what goes into Kirchoffs' rules. It's simply formalizing how currents are shared, how voltages are shared in electrical circuits. We've been talking about it when we talked about equivalent resistors. Here's now a more formal statement about how currents and voltages are shared. It's led us to 3 equations containing 3 unknowns, the 3 unknown currents, I1, I2, I3, in the 3 arms of the circuit. So now we're in a math problem. Good luck. Okay. This slide, again, packed with information, really is just me taking those 3 equations that we just made, those three equations, I've just reproduced them at the top. Plugging in the values of the resistances for R1, R2, R3, plugging in the values of the EMFs for the two batteries, epsilon 1, epsilon 2. I plug in those numbers and I plug them in here, and then I just divide it through by common factors down here. Now, normally I would totally discourage doing such things. Like we always say, don't put in the numbers. Leave it in terms of the variables until the end of the problem, then put in the numbers. The reason you would do that in a physics problem, don't put in the numbers, leave it in the variables, is that you can look at the variables and see if the equation makes sense. You can't look at the numbers and see whether the equation makes sense. So generally in physics we say don't put in the numbers, wait to the end to put in the numbers. It's more helpful. This is an exception to this because this is no longer a physics problem anymore. This is just a math problem of three equations, three unknowns. And this one I would say is an exception where I will put in the numbers because having all the R1s and R2s and epsilons there just obscures the fact that this is three equations with three unknowns, and in those three equations are just those unknowns multiplied by some numerical values. And so this slide is really just rewriting the three equations by plugging in the numbers. So I'm not walking through all of this, but this is the three equations you have. And this is what you've got to solve. Here I solved them. Here are the three values of the currents by solving these three equations. How did I do that? Well, I'm just going to tell you how I did it, just to complete the story. Again, I wouldn't ask you to do this on a test, but you might be asked to do it on a worksheet in a recitation. But anyway, how did I do it? Well, look, take a look at this top equation here. I1 plus I2 equals I3. And then take a look downstairs at these other two equations. The second equation is an equation for I2 in terms of I3. The third equation is an equation for I1 in terms of I3. I could replace I2 in this equation upstairs with this quantity here. I could replace this I1 in the top equation with this quantity here. If I was to do that, if I was to stuff this expression for I2 here, this expression for I1 here, I've got one equation, one unknown. And so I would just rearrange it and solve for I3. And so that's what I did. When I did that, I found that I3 is 0.47 amps. Once you know that I3 is 0.47 amps, well, look, it's easy to find I2 by just plugging in I3. It's easy to find I1 by just plugging in I3 again. And so the other two currents I found, the I2 with the second equation here is 0.12 amps, and I1 is 0.35 amps when I plug in I3 into this equation. And so that's how I solved it. With such a problem, as I say, it's this type of problem is prone to making sign errors. Right? It's easy to make sign errors, and look, it's not just easy for you to make sign errors. It's particularly easy since I'm much, 3 times, 4 times your age or whatever, for me to make sign errors. So I'm doing the homework last night because it was due at midnight, and there's that last problem. It's not that homework, it's the next homework I'm doing. I'm doing it ahead of time. And I keep getting the answer wrong. And it's because I kept making sign errors. And the way I knew whether I got the answer right or got the answer wrong is I took my 3 currents that I had figured out, these are the values, and I just plugged them back into the equations. If I hadn't made a sign error, then if I plug in all these numbers in these equations, then the left-hand side should equal the right-hand side. So that's a way of checking your results with these type of problems. Okay. Before I do the quiz, any questions on all that? then let's do this quiz question. It is about Kirchoffs rules, about the physics part of Kirchoffs rules. '24, so let's say 20. So I hope you can see that now. We've got a circuit in this particular problems, and we're asked to apply, let me make this bigger, Kirchoffs rule, current rule to this circuit. In particular, I'm asking you to apply the current rule at the node, remember that's a junction, at the node B. Here's the node B. So this is a node where this left-hand wire is split into two, into an upper and a lower path. The currents going in and going out are labeled. They're labeled, I don't know why this labeling exactly, but, well, I do actually. In goes I2 and out is going I1 and I24. I1 because it goes through resistor R1 and I24 because it goes through this 24 ohm resistor. But we've just got to pick which one of these four relationships or equations between the three currents is the right equation.
Because you started junction B.
I do. Yeah. And this is the. I would like to have I two say this is all positive. These two.
Yeah.
Okay, maybe I'll answer that, this question. So this is a question about the current rule. The current rule basically says that whatever current flows in must be balanced by a corresponding current flowing out. And so we're going to look at these three currents, look at which ones are flowing in and which ones are flowing out, and we've got to make an equation that has the amount flowing in equal to the amount flowing out. Now if I look at the circuit diagram, I see that I2 is flowing out of the node, I24 is flowing out of the node, I2 is flowing into the node. So there's two coming out and one going in. So for example, I could write the equation describing that node in this way. I1 is coming out. I've associated that with the plus sign for out. I24 is coming out. That's a plus sign. It's coming out of the node. I2 is going into the node. It's the opposite sign. So I put a minus sign here. You could use the other convention, actually, that coming out of the node is negative and going into the node is positive. You would get the same equation because everything would reverse. So this is also a perfectly valid equation, and it actually is the same relationship between the three currents. It's just the top equation multiplied by a -1 to flip the signs of everything. So both those equations are equivalent. Both those equations describe the relationship between the currents that are going into and out of that node. Any questions on that? Okay, last topic then. I wanted to talk about actually circuits with capacitors, resistors, and batteries. Actually circuits in which we actually charge up the capacitors using the batteries and resistors. So this is putting together all the circuit components we've been talking about. We talked about capacitors, we talked about resistors, we talked about batteries. Now we're putting all three together in this example. So it's all bringing the entire 9 lectures together in a very nice and tidy way. The other thing that's interesting about this example here, of discharging capacitors, is we started out 9 lectures ago, and for several lectures, with our charges just being kind of frozen, immobile, just sitting there and talking about the forces and potentials and fluxes of those charges. Then we moved on to circuits where we had the charges kind of steadily moving around the circuits, what we call steady state. They're in motion, but it's steady motion. They're flowing steadily around the circuit. Finally, here, we're talking about circuits when we discharge a capacitor, where there's actually kind of like a moment or an instant where there's a burst of current, a burst of movement of charge in which we charge up the capacitor or we discharge the capacitor. So these are going to be time-varying currents, time-varying charges in these arrangements, which is a new world. And this new world of time-varying currents and voltages and so on is actually what after test 2 we'll get into. And it's the new world of electromagnetism. So that's why we're kind of wrapping up with this topic. Okay, that was enough of that. I'm going to give you some equations for charging up in a capacitor and discharging a capacitor. So there's going to be, for charging up a capacitor, there's going to be an equation for the current on the plates of the capacitor as we charge it up. The charge on the plates of the capacitor and the current flowing to the capacitor. And for discharging a capacitor, which is getting the charge off the plates, there'll be an equation for the current that's flowing off the capacitor and the charge as a function of time on the capacitor. So we got 2 situations, charging a capacitor, discharging a capacitor. In each of the 2 situations, we got 2 equations, one for the charge on the plates as a function of time. It would be time dependent. One for the current flowing onto or off of the plates as a function of time. It's, again, time dependent. So that's the goal here. All of those equations are going to involve a mathematical function. I know you know it, I know you love it. It's the exponential function. So it's a very important function. It's an important function in physics, but it's also a very important function elsewhere, right? Elsewhere being like biology, elsewhere being like economics. Exponential functions come up all the time. So I just wanted to just remind you of the exponential function. And I wanted to remind you that here's the exponential function. E is Euler's constant, has this value. And the exponential function is you could write it as e to the x, or e to the plus or minus x. X could be positive or negative. I'm going to write it a little differently here. I'm going to write it as e to the t divided by tau. T is time, because we're going to be thinking about how the capacitor charges or discharges as a function of time. So our variable is not going to be x, it's going to be time. Tau, I'm dividing it by tau. You'll see why this happens later on, because there will be a characteristic time constant a length of time to charge up or discharge a capacitor, and tau is that time. But anyway, we're going to be talking about this exponential function where it's a function of time. As you probably know, there's both exponential growth and there's exponential decay. I'm showing them on the left and the right here. There's decay on the left-hand side, and there's exponential growth on the right-hand side. You can see how exponential growth really, the exponent causes a number to, the exponential causes the number to explode with time in this case, and the exponential decay causes the number to decay away to nothing with time. So that's what this kind of shapes or the nature that is described by exponential functions. So classic example of exponential growth is like the beginning of COVID and the virus. That grew exponentially. Exponential growth means that, say, in the first unit of time, you might double your population. You keep doubling your population in each next unit of time. That's an exponential growth. The increase in population is in proportion to your current population. That's exponential growth. Exponential decay, the classic example of exponential decay is kind of radioactive decay. So radioactive decay, you have radioactive atoms or nuclei. They decay away with time. They decay away in time with a rates determined by the current population. So the more of them there are, the more of them decay away. The less of them there are, the less of them that decay away. That's exponential decay. So that's what exponential functions describe. Okay, so let's look at charging a capacitor. This is the circuit for charging a capacitor. What we've got is a circuit with a battery over here, a resistor, and a capacitor over here on the right. And we've also got this switch. In this arrangement here, initially the capacitor is uncharged. There's no charge on the plates of the capacitor. Then we close the switch. When we close the switch, we complete the circuit. When we complete the circuit, current will flow from the battery, flow around the circuit through the resistor, and it's going to charge up the plates of the capacitor. And so here you see charge appearing on the plates of the capacitor. And I'm going to show you two equations, one for the charge on the plates of the capacitor, one for the current that's flowing to the capacitor, that describe this charging up of the capacitor. So they're describing mathematically this occurrence of, I built this circuit, the switch was open, the capacitor was uncharged, I closed the switch, I'm charging up the capacitor. It doesn't happen in an instant. It happens over a period of time, a certain time constant. These equations describe that accumulation of charge on the plates of the capacitor, that flow of current into the capacitor. And so let's just look at the equations. Here's the equation, and here's a picture or a graph of that equation for the charging up of the capacitor. So time is horizontal on this graph, and the charge on the plates of the capacitor, that's vertical on this graph. So this is charge on the plates versus time. If you remember, we started with no charge on the plates of the capacitor at time 0. And so we start down here. This is an uncharged capacitor at the moment we close the switch. There's no charge on the plates of the capacitor. With time, the charge will grow on the capacitor's plates, and actually it grows. The amount of charge will finally reach this value here. This is nothing other than C equals Q over V. I've just rearranged C equals Q over V for Q, the charge on the plates, in terms of the capacitance of the capacitor and the voltage that's supplied by the batteries. It's an EMF rather than a V, but it is a voltage. So we start out down here at the bottom with no charge on the plates. We're going to end up, after a long time, at this value for the charge on the plates. This equation describes that growth in charge. if you look at this equation here, it is describing a time-varying charge on the plates. Look, there's time in the exponent of the exponential here. This exponential here starts out at time 0. That exponential is 0. Sorry, completely wrong. That's the opposite. That exponential at time 0 is 1, because it's e to the minus 0 at time 0. E to the 0 is 1. And so this exponential starts out as 1, but in parentheses you've got 1 minus 1, so there's no charge on the plates. If we waited a long time, so let's wait for t to get large. Let's wait for t to get larger than this number here, RC, product of resistance and capacitance. When it gets much larger than that, then this exponent in the exponential is a big number that's negative. When it's a big number that's negative, the exponential itself becomes 0, or close to 0. And so this parentheses becomes 1, and you've got the capacitor fully charged. And so that's how the exponential actually describes this growth here. It's all controlled by a quantity called a time constant. RC is that time constant. I wrote it down here. The bigger RC, the quicker the capacitor will charge. The smaller RC, the bigger the, got that wrong too. The bigger the RC, the bigger the time constant, the slower the capacitor charges. It takes longer to charge. The smaller RC, the shorter the time constant, the shorter it is to charge the capacitor. So this is controlling how quickly or slowly the capacitor gets charged up. There's a second equation. I'm just going to show you this one quickly. There's a second equation for the current. It's this guy here. The moment you close the switch, there's a big stream of current towards the capacitor. You get this current here. But with time, that current fades away as you're charging up the capacitor. And if you wait long enough, many RCs or time constants, then the current will be 0. And so that's the charging up of the capacitor. That's how we charge the capacitor. It's an interesting example of a circuit with a resistor, a capacitor, a battery, and a switch in it. All the components we worked with. It's interesting because it's not a steady state circuit. It's a kind of fleeting change in the currents and the charges on the circuit as you charge up the capacitor. There's a similar pair of equations for the discharging of a capacitor. So let me just end up by showing you those two equations. Here's the circuit for discharging a capacitor. You know there's no battery now, but I've still got a capacitor, I've still got a resistor, and I've still got a switch. But this time I'm starting with my capacitor's plates charged up with positive and negative charge. If I close the switch, then the negative charge, the electrons can run around the circuit and cancel out the positive charges. So when I close this switch, this capacitor will discharge. That takes a bit of time. That doesn't happen in an instant, in a moment. It takes some time. It's characterized again by a time constant, by a time scale that is again actually RC, the product of the resistance and the capacitance. And when I close the switch, this guy's going to discharge by having electrons flow around the circuit to neutralize the positive and negative charges that are initially on the plates of the capacitor. So let me show you the two equations for the discharge of the capacitor. Here's the discharge of the capacitor. We start out with the capacitor charged with charge Q. We shut the switch, and that charge on the plates of the capacitor, that charge falls exponentially with time. And if we waited a long time, meaning lots of RCs, lots of time constants, it becomes 0. It's described by this little equation here. Again, it's involving the exponential function with a negative exponent. It again involves a time constant that's the product of the capacitance and the resistance. There's also an equation for the charge as a function of time. It's actually the same expression as the charging up of the capacitor. It's this equation here. Again, it involves an exponential with a negative exponent describing the time dependence and an RC time constant that depends on the resistance and the capacitor. Okay. We covered equivalent resistances and solving circuit problems. We covered Kirchoffs rules, solving circuit problems, and we covered this last topic, putting together all the components of the circuit that we met: resistors, capacitors, batteries, switches, the charging up and the discharging of capacitors. Good luck in preparing for test 3.